Okay, so now the last block that remains for us to be studied is of the form, it's of the following form. Okay, again, the plus minus 1 just signifying whether it's a 0 or a pole respectively. So what are the critical points for this? Let us consider at omega is equal to omega n. We have m of omega is equal to square root of 1 minus omega square by omega n square whole square plus 4 zeta square omega square by omega n square is equal to, so this part simply vanishes because omega is equal to omega n. So what we are just left with is then 2 zeta. So I must also clarify that this is also to the power plus minus 1. So it's 2 zeta to the power plus minus 1. Yeah. So if it's a pole, then it's 1 by 2 zeta. If it's a 0, then it's 2 zeta. Okay. So these are the values that it can assume at omega is equal to omega n. Now suppose omega is much smaller than omega n, then m of omega is simply going to be equal to 1, because both this term and this term, they become negligible. Similarly, for omega much greater than omega n, now remember this 1 then becomes insignificant, whereas this omega over omega n then assumes significance. But even so, omega over omega n square is much more significant than omega over omega n. Yeah, and since we are considering complex poles or zeros, therefore zeta is less than unity, so this becomes even smaller. Yeah, as 2 is of course just a scaling factor. Anyway, the point is that this is a square, so it essentially assumes the characteristics of omega square by omega n square. That's what m omega approximately is. Okay, I should use the approximation signal sign here also. Okay, so therefore this is equivalent to 0 dB as before. What is this equivalent to? This is equivalent to 40 log of omega over omega n. So therefore you can see, again, this will have plus minus, this will have a power of plus minus 1. I keep forgetting to write this. So therefore the slope of this asymptote, now you know what the asymptote is, because now we've seen what the first order poles and zeros behave like. So therefore it makes sense if we just directly talk about asymptotes. So the high frequency asymptote rises or falls at a rate of plus minus 40 dB per decade, whereas the low frequency asymptote is just the constant 0 dB line like we had in the case of the first order factors. Okay, notice another interesting thing. If you extrapolate this approximation and apply omega is equal to omega n, this reduces to 0. So therefore both the high frequency and the low frequency asymptotes intersect at omega is equal to omega n. So similar to first order terms, high frequency asymptote and low frequency asymptote intersect at breakpoint omega n. So over there the breakpoint was tau omega is equal to 1. Yeah, here it is omega n. All right. So now we have the picture at least about the behavior of m omega. That really doesn't answer the question in its entirety, because we still have to find out what the behavior of the phase function is. Okay. Oh. Okay. So now we want to find out what this phase function looks like for this. Now this, I must warn you, is not really very handy to deal with. Yeah, it's not very straightforward. So and the reason is because this not only depends on this omega or omega n, but also on the zeta. So the zeta assumes significance when you're talking about the phase, because remember, the exact expression of the phase, if I am to write it down, what is it going to be? It is going to be tan inverse. Go back to the previous slide. So what's the real part? The real part is 1 minus omega square by omega n square. Okay. And the imaginary part is 2 zeta omega by omega n. This is going to be 2 zeta omega over omega n upon 1 minus omega square by omega n square, which is equal to tan inverse, just multiplying above and below by omega n square, we get 2 zeta omega omega n upon omega n square minus omega square. All right. So once again, as before, you can see that as omega is much smaller than omega n, or rather I should write as, let's write this as, let's say, if, then phi omega can be approximated as 0. All right. Okay. As omega tends to omega n, phi omega tends to, you can see it tends to infinity, the argument inside the tan inverse, this tends to pi by 2 or 90 degrees. So now the next question. As omega tends to infinity, what happens to phi omega? Yeah, that is the question we need to seek the answer to. So what do we do? Look, first of all, if you divide above and below by omega square, I'm sorry, so then you have is equal to limit omega tending to infinity tan inverse 2 zeta omega n by omega upon omega n square by omega square minus 1. So you see, as omega tends to infinity, the numerator vanishes to 0 unambiguously. What happens to the denominator? So it just tells you that the denominator has a negative real part. Okay, so this tends to 180 degrees. Okay, so this is what we have ascertained. But what about the behavior in between? How does it rise and fall with zeta? That picture is not really clear from here. So we'll rest our case here for this, and we'll see by plotting while plotting, how do we argue about this? How do we reason about this? Because apparently from all this expression, the zeta doesn't enter the picture, but we know, at least in the time domain responses, we have seen that the zeta plays a very key role. So it stands to reason, therefore, that all these plots should have some, the zeta should have some bearing on all these plots, both the magnitude and the frequency plot. Of course, the phase plot. Of course, for the magnitude plot, we've already seen that the zeta manifests itself as the magnitude at omega is equal to omega n. Okay. But in the phase plot also, it should have some effect. How would we see that effect? Okay, so let's do a couple of quick calculations here. Let's draw a line below this phase. Okay, maybe I'll not do this. I'll leave this as an exercise to you. So you have to prove that the max or min of m omega is equal to omega, sorry, I should rewrite this. Yeah, 1 minus omega squared by omega n square whole square plus 2 zeta omega over omega n whole square, yeah, whole to the power half, actually plus minus half, depending on whether it's a pole or a zero. So let me just clarify that. Plus minus half occurs at omega is equal to omega n square root of 1 minus 2 zeta square. So clearly, if you can prove this, then you'll see that obviously this peak doesn't exist for all values of zeta. In fact, this will only exist for zeta belonging to this domain, yeah, 1 by root 2, which is 0.707, yeah, and is equal to, I think it is, if I am not mistaken, 2 zeta, please verify this, to the power plus minus 1. So this is an exercise. We might put it in a tutorial sheet, but nevertheless this is an exercise and you should definitely try this. Okay, it's not very difficult. You just have to differentiate this function once and just verify. It's really quite straightforward, I must say. The interesting thing here is that note that at omega is equal to omega n, if you remove this part, if you remove this part, at omega is equal to omega n, we know that the magnitude is 2 zeta to the power plus minus 1. Now when you correct this, so essentially what it means is that omega is equal to omega n, the value that it attains is not necessarily the maxima. So that is at least something. In fact, the maxima occurs a little ahead of the breakaway frequency, which is omega n. And the magnitude is also different, is it not? Yeah. So that is an interesting take-home message here. Okay. So that is exactly the reason why I insist that you should try this exercise. You should try to solve this exercise on your own. Okay. Enough of that. But we still haven't addressed really the main question. This was just a small digression. We still haven't addressed this main question as to how zeta influences this plot of this phase. Is it very obvious to see? Can we just ascertain this by looking at the function here? Because we have only looked at these regions when omega is much smaller than omega n, when omega is almost equal to omega n, tends to omega n, and when omega is much greater. Okay, and we have seen that it attains these values. So these two experience with first order factors tells us that these two will only give us certain asymptotes. Yeah, and this will give us some value in between. But how it goes about, how it rises or falls, how steeply the exact phase plot rises or falls is not a very straightforward question to answer, it turns out, isn't it? So how do we deal with that? Okay, so let's try to look at that in the next slide. Okay, so as before, draw this. Okay, that straight line came out much straighter. Once again, we are trying to do for the second order factor. I'm not going to write it here because there's a shortage of space here. Second order factor, that omega n is equal to what should I choose? Let me think. What sort of an omega n should I choose here? Let me choose omega n is equal to 1. Of course, you can choose anything else also, it really doesn't matter. Alright, so let me just choose omega n is equal to 1 here for the genericity. Okay, fine. So we start from 0.001 as we've always done, 0.01, 0.1, 1.0, 10.0 and 100.0. Okay, and here we have the 0 dB line. So this is 20 log m omega in dB, and this is phi of omega in degrees. All right, this is 0. Let's say this is 20, minus 20, this is minus 40, so this is minus 60, this is 20, 40, 60. All right, fantastic. Now we have a 0 here. Okay, let me just rectify that. Oops, I just erased the best straight line I've drawn so far in this lecture, and probably I'm going to replace it with a much worse. Yeah, as expected. All right, never mind. This is 0, this is minus 90, this is minus 180, this is 90, and this is 180. Right, so we have chosen this to be our critical frequency, the break frequency, the break. Okay, let me just put these points here, same as we've been doing throughout. Okay, so we know, what do we know about these phase plots? So we know that at these points, let me use the convention here, it's 90 degrees. Green one here, it's minus 90 degrees. And once again, as before, we start by drawing the lower frequency asymptotes, and how far do we go with that? Okay, so here we will not really bother too much with those corrections here. Mostly we shall be concerned with drawing the I'm sorry, drawing the graph accurately. So let me just go up to 1/5 the way up, maybe a decade up. I'll just go a decade up here. Remember, this is completely arbitrary. Okay, as it is when you're drawing asymptotes, it's an approximation. So as I said, some books go up to 1 decade above, below, and 1 decade above. Some books go 1/5 of the break frequency below, or 1/5 of, and 5 times the break frequency above. So let me just draw it. Yeah, let me just draw it till here. All right, and use the red line here. Okay, here. So that's the high frequency for the 0, and the green one, that's the one for the pole. Okay, so let me just join this. This is pretty straightforward so far, but remember, the reason why we are slightly uneasy with this is that we have two parameters, omega n and zeta. This only accounts for the contribution due to omega n. So how does it actually bend around this? Yeah, that is an important question to ask. And how do we infer? So the question before us is, how does zeta affect the exact plot? That is the question we are interested in answering here. All right. So it goes from 0 to plus 180 or 0 to minus 180 through plus minus 90 at the break frequency. Okay. But how does it go? So it could, see, there are several ways. One of the ways could be, it could just go simply like this, and like a first order system, it would go like this. Yeah. Or it could just go like this, go cross over this asymptote once, then cut across the asymptote once, and then cut across again, and then go like this. Okay. But what should be the exact pattern? So one of the options is, let me just point out the options. One of the options is it could be something like this. Okay, let me erase that now. Oh, I ended up erasing more than I wanted to. Never mind, I can draw that again. Okay. Yeah. The other option is, yeah, you see that, right? It could go like this. Oh, sorry. Yeah. The other option is that it could start about like this, cross the asymptote once here, then pass through this, and then again cross here and go like this. Moreover, to what extent do we need to correct it? Could it be a correction like this, or would it be a correction like something like this? In other words, would it be very steep, or would it be rather flat? Now this is where the zeta comes in. I would like to point out that this is where the zeta comes in. So I'll erase these lines. Hopefully one stroke of the eraser should suffice. Ah, good. Excellent. Right. So the point is, how does zeta influence this? Now in order to understand that, let us go to the next slide. What you have to remember therefore is, as zeta tends to 0, what happens? What is the behavior of that phase function as zeta tends to 0? Yeah, think of this. What happens as zeta goes to 0? So as zeta goes to 0, see, this remains a 0 here, and then suddenly it acquires a 0 by 0 sort of a form, isn't it, at 90? So it's like a step. You, at least intuitively, you should try to visualize this, isn't it? See, when zeta is 0, there's always a 0 sitting here. So the imaginary part is 0. But the real part also becomes 0 at omega is equal to omega n. So it's a 0 by 0 form, which essentially means that this goes to around, I'm sorry, 90 degrees. Okay. And soon thereafter, if you approach it from one side, it is approaching from the 0 side. And then if you look at this asymptote here, it is still this 180 degrees, isn't it? So on the lower side it is 0, on the higher side it is 180, irrespective of what zeta is. Okay. And in between it causes a transition at omega is equal to omega n. It approaches on the left side from the lower end. So in other words, this gives the picture of some sort of a step function. As zeta tends to 0, we expect this function to behave in a manner such as this. Let's say this is omega n. It will behave something like this. This is 0 degrees. This is, let's say, 180 degrees, and let's say we are considering I'm sorry, I should have put a plus minus here also. Yeah, I keep forgetting this. Because we have a plus minus 1 here. So I should put a plus minus 1 here. Just notice that. So anyway, now we are considering the plus 1 case. So what happens is at omega n, suddenly there is like a jump. It's like a step jump. So this tells you that as zeta has very small values, this seems to be very steep. Okay. But as you keep increasing zeta on the other hand, this probably flattens out to something like this. So using this particular intuition, we can say that you will get all these sort of curves. You will get something like this, which rises very steeply. Maybe this one corresponds to zeta 1. And then you have another curve. Another color, should I? Maybe a thinner line? I don't know. I don't see how it's thinner. So the one that is less steep, say this corresponds to zeta 2. Then we can safely say that zeta, of course the same thing will follow for the pole as well. So then we can safely say that zeta 1 is less than zeta 2. So as you keep increasing zeta, this curve flattens out. Okay? And as you decrease zeta, this approaches an exact step function. It tends to have a jump-like feature. So that is the one intuition that you can draw from the effect of zeta on the face. So what about the magnitude then? All right. So the magnitude, once again we draw this, the low frequency asymptote. Oops, again I did it. Okay, not so bad. Managed to recreate most of it. What about the high frequency asymptotes? The high frequency asymptotes will now be 40 dB per decade. So remember that. Yeah, it's 40 dB per decade. That's how it will go up, and that's how the other fellow will come down. Yeah, so this is now plus 40 dB per decade, and this is minus 40 dB per decade. And they'll, as I pointed out earlier, they'll meet. So there's a continuity in the phase plot, in the magnitude plot, I'm sorry. Because if you extrapolate this back at omega is equal to omega n, this is just 0 dB. So these two asymptotes intersect at this break frequency. Once again, for most purposes, this sort of suffices. But if you want to be exact about this, now that other part will, this exercise that we've given you will assume some significance. Apart from that, we also know that at omega is equal to omega n, if you have to introduce a correction, it's actually equal to either 1 by 2 zeta or 2 zeta. So if it's a pole, then it's 1 by 2 zeta, which is less than 1. So in the dB scale, it will come below 0. Yeah. So it's 1 by 2 zeta. So what sort of a value does 1 by 2 zeta assume? Let me erase this. 20 log 1 by 2 zeta. What's a typical value? Let's say zeta it's an underdamped system. Let's take zeta is equal to 0.8. So that means this is equal to 20 log to the base 10. It's 5 by 8, is it? Yeah. So log 5 minus log 8. Anyway, whatever it is, you better evaluate that. So it's something negative. It's a negative value. That's clearly obvious from this, is it not? Okay. Okay. So then remember that this is a good sufficient amount of damping. Okay. There's a good sufficient amount of damping involved here. For that, I'm sorry, if you consider this pole here, there's going to be something negative. So if you want to introduce a correction here, you have to probably make it pass through a point such as this. Is it not? So that is how this will look. Once again, you have to make some approximations here, but essentially the plot would look something like this. But does it mean that does it mean that all these plots will look like this? We have clearly seen in this exercise that there will be certain peaks. At least for some ranges, there will be peaks, right? So we cannot expect that irrespective of whatever value we choose here, this will just decay, right? So let us say we choose zeta is equal to 0.5. Then 20 log of 1 by 2 zeta is equal to 0. So then it matches with the corner frequency exactly. So there is no need for any correction in that case. That is what this reveals, apparently. But remember, this exercise that I've just given you tells us that there is a peak which precedes omega n. And at this peak, the value is not really 1 by 2 zeta, but rather a little more than 1 by 2 zeta. So what is this value? Let me just try this. 20 log of 1 by 2 zeta root 1 minus zeta square. What will this value be? Is equal to 20 log 1 by 1 minus 0.25. Now you can see that this is positive because this is square root of 3/4, which is 2 by root 3. Yeah, so which is more than 1. So when you pass an argument more than 1 inside the logarithm, this is positive. So therefore the peak value, this one we had drawn for zeta is equal to 0.8. But now the moment you make zeta is equal to 0.5, even though it passes through this corner frequency with a value of 0 dB, but preceding the corner frequency, just a while before the corner frequency, it must have had a peak somewhere here, isn't it? So then the exact plot would be something like this. If we make it even lesser, let's say we choose zeta, let's choose something drastically lesser. Zeta is equal to 0.05. This is really going to be very high. Then we are looking at 20 log of so 0.05, 0.1, 10 over, okay, we can almost assume this to be 1, is it not? Yeah. Yeah, I guess so. Yeah, so this is almost equal to 20. You see that? So for lower values of damping, and of course the peak will also be shifted accordingly. The peak frequency will correspond to that is omega n root over 1 minus 2 zeta square. So zeta square is 0.0025. That's okay, it's closer to omega n. Not a problem then. Yeah. So this will shift closer and closer to omega n. The interesting thing is that the peak now rises significantly. Now you'll have a peak of around 20 dB and then eventually coming down like this. So this is probably for zeta is equal to 0.05. You see what happens as you decrease damping, you tend to have higher and higher peak values. Now this peak value that is attained here for the pole is called the resonant peak, MR. Of course, needless to say, I'm not drawing it because I don't want to make this figure too congested. You can draw red lines similar to the green lines I've drawn corresponding to the zeros. It will be exactly in the same manner. Yeah. So nevertheless, this is what we call the resonant peak. This is again another term that you will encounter quite often when dealing with systems. So now you understand what it implies. When you draw a Bode plot, the Bode magnitude plot, wherever it attains a peak. See, so far whatever plots we have seen, the first order factors or the constant or the integrator, they have been monotonic or constants or flat more or less. Yeah. But now you tend to see these peak sort of behaviors, and these are typical of these second order factors. And that is why when you encounter such systems, you have something called a resonant peak, which is MR. Okay. So you remember in the last regular lecture that we had, I told you that this frequency domain analysis will allow you or sort of enable you to see a lot of things or visualize a lot of things that you've only heard names of, and you've just known that, okay, this is something that we call this, but you really don't understand why we call them that. So now you see that this peaking is happening here. So it's called a resonant peak. Okay. All right. So when someone tells you, so when someone tells you that this has certain resonant peak, you can actually infer information about the zeta. Just like in the time domain, you can infer about the value of zeta based on the peak overshoot of the time domain response. In the frequency domain, anyone who tells you information about the resonant peak is indirectly telling you information about the value of zeta. But remember, there's a crucial difference here. This is not really something that exists for all underdamped systems. Unlike in the time domain, where you will have these peak overshoots for all values of zeta within the range of 0 to 1. In the frequency domain, the resonant peak will only exist for 0 to 1 by root 2, or that is 0.707. So do not try to really map them one-on-one and say that this is exactly equivalent to that. It's not. It's just another way. So in frequency domain, we have different handles to specify systems, and in time domain, we have different specifications. So in frequency domain, similarly, if someone wants to specify the zeta indirectly, they'll just say, okay, that we have such and such resonant peak, and you'll immediately know that, okay, if that's the resonant peak, then this must be the damping of that particular system. Okay, so that is MR. Now we have seen each of those constituent blocks that go into the making of the entire composite system. We have seen the integrator, we have seen the constant gain, we have seen the first order terms, and we have seen the second order terms with complex roots. Okay, so we know how to plot each one of them individually. All right. So now it's time to move over to take an example. Now we will next consider an example. Okay. So let me take this example. So final word before we conclude, all of this has revealed to us that if we are given a particular G of S, then we know how to sketch its Bode plot. Remember, we started motivating this topic by saying that it's quite the contrary. If you're given a black box, which you know to be some LTI system, you are allowed to perform experiments where you apply sinusoids, cosinusoids, like so, and you get the yt is equal to a m omega cos omega t plus phi of omega. So you measure the phase shift on an oscilloscope. If this is your input waveform, and if this is your output waveform, of course the frequencies are the same as it's an LTI system, then this tells you phi at that particular omega, and if this is the inputs level and this is the outputs level, then the ratio will tell you m of omega. So you carry on doing this by applying different sinusoids of different frequencies. So suppose you choose omega 0, omega 1, omega 2, so on and so forth, over a sufficiently large range of frequencies that are of interest to you. Then at least within that range, you can get those points. And then you sketch. So in the actual problem, you will basically sketch some plot like this. This will be your m omega, and this will probably be your phase. And then you have to infer what the system's poles and zeros are. So you have to basically draw these tangents, approximate them as some asymptote, measure their slope, whether it's 20 dB per decade or 40 dB per decade, join those, obtain the corner frequencies, find out where the poles and zeros are and what their multiplicities are, and from the phase plot, so it appears as if from the magnitude plot you can infer everything. But remember, that is not quite true. The reason being that 1 minus s upon 1 plus s, this transfer function has exactly the same magnitude plot as gs is equal to 1. Yeah. So if you look at just the magnitude plot, there's no way you can distinguish between these two. Okay, so in the next class we shall see that without the phase plot you cannot really determine uniquely what the transfer function is, and this is what brings us to the notion of what is called non-minimum phase systems. We have used this term so often in our class till now when we are dealing with time domain methods, but now this will begin to make sense and we will explain why systems which have right half plane zeros are called non-minimum phase systems. So that is a topic for the next lecture. Thank you.